Swayam Prabha. Digital India. Educated India.
Welcome to the lecture 14 of the course on time series modeling and forecasting. In this lecture, I will discuss about the mixed ARMA processes. In earlier two lectures, we discussed the moving average processes and autoregressive processes. In moving average processes, Yt is generated by, or the current observation Yt depends on the past shocks, or you can say the shocks connected with the past observations. It does not depend directly upon the past observations, but it depends upon past observations through the shocks involved in those observations. In autoregressive models, the current observation Yt depends upon the past observations directly, but it does not depend upon the past shocks, the shocks connected with the past observations. Now, mixed ARMA models contain both kind of terms, means in mixed ARMA models, the current observation depends upon the past few observations directly as well as past shocks. Now, before considering the ARMA models, first we derive the partial autocorrelation function for the moving average processes. In particular, in this example, I am going to consider the MA1 process Yt equal to Ut plus theta 1 Ut minus 1. So, for MA1 process, for k greater than or equal to 2, rho k is equal to 0, and for k equal to 1, rho 1 is equal to theta 1 upon 1 plus theta 1 square. Now, for obtaining the partial autocorrelation function, obviously A11 is equal to rho 1, which is theta 1 upon 1 plus theta 1 square. Then A22, we use this formula for calculating the partial autocorrelation functions. So, A22 is equal to 1 rho 1, and then you have rho 1 rho 2. And since for MA1 process rho 2 is equal to 0, so in the numerator you get the determinant 1 rho 1 rho 1 0, and in the denominator we get the determinant 1 rho 1 and rho 1 1, this part or this part you can say. Now, the value of denominator is 1 minus rho 1 square, and the value of numerator is, here you get 1 into 0 minus rho 1 square. So, you get minus rho 1 square. So, finally, you obtain minus rho 1 square upon 1 minus rho 1 square, which is less than 0 for all values of rho 1 or for all values of theta 1. Does not matter whether theta 1 is positive or negative. Then for obtaining A33, we adopt the similar procedure. A33 is equal to determinant value 1, rho 1, then you have rho 2 here, but for MA1 process rho 2 is equal to 0. Then you have rho 1 here, 1, rho 1, and the third column is rho 1, rho 2, rho 3, so on. You have rho 1 here, rho 2 is equal to 0, rho 3 is equal to 0, divided by the determinant of 1, rho 1, 0, rho 1, 1, rho 1. Then you have rho 2 here, rho 2 is equal to 0, then rho 1 and 1. Then you can easily simplify it. So, in the numerator you obtain rho 1 cube, and in the denominator if we solve this determinant, then we obtain 1 minus twice rho 1 square. So, A33 is equal to rho 1 cube upon 1 minus twice rho 1 square. You can also calculate A44 in a similar manner. A44 is actually equal to, you have 4 cross 4 determinant, 1, rho 1, rho 2 is 0, rho 3 is 0. Then rho 1, 1, rho 1, rho 2 is 0. Then you have rho 2 here, rho 1, 1, rho 1. And then you have the last column, rho 1, rho 2, rho 3, so on. So, you have rho 1 and rest of the elements are equal to 0, divided by the determinant 1, rho 1, 0, 0, rho 1, 1, rho 1, 0, 0, rho 1, 1, rho 1, and then you have rho 4, which is 0, rho 3, 0, rho 2, 0, sorry, this column is, you have 0 here, 0 here, then rho 1 here and 1. And then you solve this the numerator and the denominator, and finally you obtain A44 equal to minus rho 1 to the power 4, 1 minus rho 1 square whole square minus rho 1 square. So, this is the expression for the fourth partial autocorrelation function. Now, remember that for MA1 process, the autocorrelation function vanishes for k greater than or equal to 2, but partial autocorrelation function never vanishes. Now, here I have plotted the ACF and PACF for MA1 process, yt equal to ut plus 0.7 ut minus 1. So, you observe that the ACF vanishes, the first autocorrelation is non-zero, rest are equal to 0. But partial autocorrelation function, it oscillates between positive and negative values. It never becomes 0. Similarly, for MA2 process, we have taken y t equal to u t plus 0.7 u t minus 1 plus 0.2 u t minus 2. Again, the autocorrelation function is non-zero up to k equal to 2, and then it becomes 0. Whereas the partial autocorrelation function, it is positive here, then becomes negative, remains negative, then it rotates between positive and negative values, but it never vanishes. Now, this is a special characteristic of ACF and PACF of moving average and autoregressive processes. I have also taken the autoregressive processes AR1 as well as AR2, and you observe that for AR1 process, this is the ACF, it never vanishes, but PACF vanishes after k equal to 1. Similarly, for AR2 process, the ACF never vanishes, but PACF vanishes after k equal to 2, it becomes 0. So, this is something interesting for moving average processes. The autocorrelation function vanishes after a certain point, but partial autocorrelation function never vanishes. However, for the autoregressive processes, the autocorrelation function never vanishes, but partial autocorrelation function vanishes after a certain point. In fact, the cutoff point after which the partial autocorrelation function becomes 0 is the order of the autoregressive process. Now, this particular property of ACF and PACF of autoregressive and moving average processes plays important role in identifying these processes and also identifying the order of these processes. Now, we consider mixed autoregressive moving average process of order P q. We denote it by ALMA P q process. AR means it has autoregressive terms, and order of the autoregressive term is P, and then it has moving average terms of order Q. So, it contains P autoregressive and Q moving average terms. Then the process is defined as y t equal to delta plus phi 1 y t minus 1 plus phi 2 y t minus 2 plus so on plus phi p y t minus p. So, the past p values of y's are involved. Then for u t, of course, the current shock is involved here, and along with that past q shocks or the shocks connected with the past q observations are also involved. u t minus 1, u t minus 2, so on u t minus q. So, the model involves p lagged values of y's and q lagged values of u. If you take expectation of y t, then expectation of y t is equal to say mu, then if we take expectation on both sides of 1, then we have say expectation of this y t is mu, you have delta here plus phi 1, expectation of y t minus 1 is mu plus phi 2, expectation of y t minus 2 is mu, so on, plus phi p, expectation of y t minus p is also mu. Then expectation of all these terms is equal to 0. So, you obtain mu equal to phi 1 mu plus phi 2 mu, so on, plus phi p mu plus delta. And then you collect all the terms involving mu on the left hand side. You get mu into 1 minus phi 1 minus phi 2, so on, minus phi p equal to delta, or mu is equal to delta upon 1 minus phi 1 minus phi 2, so on, minus phi p. So, you obtain this expression for the mean of the process. So, this is the mean. For delta equal to 0, mu becomes 0. So, the mean of the process becomes 0 for delta equal to 0. Now, in terms of the backward shift operator, suppose you collect all the terms involving y on the left hand side and all the terms involving u on the right hand side, then you have 1 minus phi 1 b minus phi 2 b square, so on, minus phi p b to the power p y t is equal to delta plus 1 plus theta 1 b plus, on the right hand side we have delta plus 1 plus theta 1 b plus theta 2 b square and so on, plus theta q b to the power q u t. Now, suppose capital phi b denotes the operator 1 minus phi 1 b minus phi 2 b square, so on, minus phi p b to the power p, and capital theta b denotes the operator 1 plus theta 1 b plus theta 2 b square, so on, plus theta q b to the power q. Then the ARMA PQ process given in equation 2 can be represented as phi b y t equal to delta plus theta b u t. So, we write the process in this form. You remember that in an earlier lecture we discussed the Wald representation, and at that time we considered two different Wald representations for the time series. One was based on a polynomial of infinite degree in lakhs. So, here summation j equal to 0 to infinity theta j b to the power j is a polynomial of infinite degree in B. So, it is actually infinite like polynomial. Then this infinite like polynomial can be approximated by the ratio of two finite like polynomials. So, here actually I have slightly changed the notation, and I have represented this infinite like polynomial by psi b, and then you can write this psi b equal to theta b upon phi b. Both theta b and phi b are polynomials of finite order. Theta b is a polynomial of order q in backward shift operator b, and phi b is a polynomial of order p in backward shift operator b. Now, this representation actually forms the basis of ARMA processes. Using this representation, you can write y t in the form of ARMA process. So, this ARMA representation actually approximates the dynamic of any purely non-deterministic weakly stationary process. In the Wald representation, initially we represented any purely non-deterministic weakly stationary process as a moving average process of infinite order, and then you can further approximate this moving average process of infinite order, or you can further approximate the polynomial involved in this moving average process of infinite order by the ratio of two polynomials, and both of those polynomials are of finite order. So, thus you can say that this ARMA representation approximates the dynamic of any purely non-deterministic weakly stationary process. Then it describes a weakly stationary process in terms of two polynomials, one for the autoregressive and other for the moving average, but both of these polynomials are of finite order. So, if you have autoregressive process of very high order, or you have moving average process of very high order, then these processes will involve a large number of parameters. You have autoregressive process involving a large number of parameters. You can approximate that autoregressive process of involving large number of parameters, the autoregressive process of very high order, by an ARMA process of much lower order and with much lesser number of parameters. Similarly, suppose you have a moving average process of very high order. Again, you can approximate the polynomial involved in that moving average process by the ratio of two polynomials of much lower order, or you can approximate the moving average process by ARMA process of much lower order, and this ARMA process involves much lesser number of parameters. So, you can approximate a process involving a large number of parameters, an autoregressive process or moving average process, by an ARMA process involving much smaller number of parameters. So, that is the advantage of using ARMA processes. Now, we consider ARMA 1 process. So, P is equal to 1, Q equal to 1, and we take delta equal to 0. So, your process is y t equal to phi 1 y t minus 1 plus u t plus theta 1 u t minus 1. The variance of the process is given by, say, gamma naught equal to expectation of y t square So, we take expectation of phi 1 y t minus 1 plus u t plus theta 1 u t minus 1 whole square. Then by taking square of this quantity, you obtain phi 1 square y t minus 1 square plus u t square plus theta 1 square u t minus 1 square, and then you get cross product terms 2 times phi 1 y t minus 1 u t plus 2 times phi 1 theta 1 y t minus 1 u t minus 1 plus 2 times theta 1 u t minus 1. Obviously, the expectation of this term is 0. Expectation of y t minus 1 square is again gamma 0. So, you have phi 1 square gamma 0 here. Expectation of u t square is equal to sigma square u, then plus theta 1 square, again you have expectation of u t minus 1 square, which is sigma square u, plus 2 phi 1 expectation of y t minus 1 u t plus 2 phi 1 theta 1 expectation of y t minus 1 u t minus 1. So, then we have to evaluate these two expectations, expectation of y t minus 1 u t and expectation of y t minus 1 u t minus 1, and then we substitute the values of those expectations here, and then we will try to find out the values of gamma naught. Now, expectation of y t minus 1 u t is equal to 0, because y t minus 1 in this equation 5 of ARMA 1 model, you just replace this t by t minus 1. So, you get y t minus 1 equal to phi 1 y t minus 2 plus u t minus 1 plus theta 1 u t minus 2. So, y t minus 1 does not depend on u t. Y t minus 1 and u t are uncorrelated. So, expectation of y t minus 1 u t is equal to 0. Then the next term which you have to obtain is expectation of y t minus 1 u t minus 1. Then you can write y t minus 1 equal to phi 1 y t minus 2 plus u t minus 1 plus theta 1 u t minus 2 into u t minus 1. Now, expectation of y t minus 2 into u t minus 1 is 0, expectation of u t minus 1 square is equal to sigma square u, and expectation of u t minus 2 u t minus 1 is 0. So, finally, you obtain expectation of y t minus 1 u t minus 1 equal to sigma square u. So, we substitute the values of these two expectations in equation 6, and then finally, you can write 6 as gamma naught equal to phi 1 square gamma naught plus sigma square u plus theta 1 square sigma square u plus twice theta 1 phi 1 sigma square u. Again, you take this term phi 1 square gamma naught towards the left hand side. So, you obtain gamma naught into 1 minus phi 1 square here, and then you divide by 1 minus phi 1 square. So, what you get? Gamma naught is equal to sigma square u 1 plus theta 1 square plus twice theta 1 phi 1 upon 1 minus phi 1 square. So, this is the value of gamma naught, or this is sigma square y. Again we obtain gamma 1, which is equal to expectation of y t minus 1. Then we write y t equal to phi 1 y t minus 1 plus u t plus theta 1 u t minus 1, and we multiply it by y t minus 1, and then we take expectation. So, expectation of the first product is phi 1 into expectation of y t minus 1 square is gamma 0. So, you get phi 1 gamma 0 plus expectation of u t y t minus 1 we have already obtained, this is equal to 0. Then you have theta 1 expectation of u t minus 1 y t minus 1, again this expectation we have already obtained, and the value of this expectation is sigma square u. So, you obtain gamma 1 equal to phi 1 gamma naught plus theta 1 sigma square u. Now, you simply substitute the value of gamma naught in this expression from this equation, equation 8. So, you substitute this value of gamma naught in this expression for gamma 1, and finally, you obtain sigma square u phi 1 plus theta 1 plus phi 1 theta 1 square plus theta 1 phi 1 square divided by 1 minus phi 1 square. So, this is the value of gamma 1, and you can further simplify it. You look at these two expressions. If you take phi 1 theta 1 common, then again you obtain phi 1 plus theta 1 here. So, then you have phi 1 plus theta 1 here also. So, you take phi 1 plus theta 1 common, and inside you get 1 plus phi 1 theta 1. So, this is the expression for gamma 1, the first auto covariance. Now, gamma 2 is equal to expectation of y t minus 2. Then you write y t equal to phi 1 y t minus 1 plus u t plus theta 1 u t minus 1, and you multiply it by y t minus 2, and then you take expectation. So, expectation of this term phi 1 expectation of y t minus 1 y t minus 2 is equal to gamma 1. Expectation of u t y t minus 2 is 0, and expectation of u t minus 1 y t minus 2 is also 0. So, you get gamma 2 equal to phi 1 gamma 1. And generally, if you take gamma k, the kth autocovariance, which is equal to expectation of y t minus k, and then again you write y t equal to phi 1 y t minus 1 plus u t plus theta 1 u t minus 1. You multiply it by y t minus k. Then you get phi 1 expectation of y t minus 1 y t minus k, and expectation of y t minus 1 y t minus k is equal to gamma t minus 1 minus t minus k. So, this is equal to gamma k minus 1, the autocovariance of lag k minus 1. Expectation of the second term, expectation of u t y t minus k is equal to 0, and expectation of u t minus 1 y t minus k is also equal to 0 for all k greater than or equal to 3. So, ultimately you get gamma k equal to phi 1 gamma k minus 1, or you can write it as phi 1 square gamma k minus 2 equal to phi 1 cube gamma k minus 3 and so on. So, what happens for k equal to 1, the expression for autocovariance is this. After that, the autocovariance function of alpha 1 process starts behaving like the autocovariance function of AR1 process, because the effect of MA term is of order 1. So, the effect of MA term on autocovariance function vanishes after the first lag. So, after the first lag it starts behaving just like the autocovariance function of AR1 process. Then you can easily obtain the ACF of alpha 1 process also, which is equal to rho 1 equal to gamma 1 upon gamma 0, and then in the numerator you have phi 1 plus theta 1 plus phi 1 theta 1 square upon 1 plus theta 1 square plus twice phi 1 theta 1. And for k greater than or equal to 2, rho k is equal to phi 1 rho k minus 1, which is phi 1 square rho k minus 2 and so on, phi 1 to the power k minus 1 rho 1. So, after k equal to 1, it just starts behaving like the autocorrelation function of AR1 process. It decays exponentially, but never vanishes. So, this is how the autocorrelation function behaves. If phi 1 plus theta 1 is greater than 0 and both if phi 1 is also greater than 0, then rho k is greater than 0 for all k, because if phi 1 plus theta 1 is greater than 0, then rho 1 is greater than 0, and since phi 1 is greater than 0, rho k remains greater than 0 for all k. Now, if phi 1 plus theta 1 is less than 0, then obviously rho 1 is less than 0, and if phi 1 is greater than 0. So, this part always remains positive. So, sign of rho k depends upon the sign of rho 1, and rho 1 is negative. So, in that case rho k is negative for all k. If phi 1 plus theta 1 is greater than 0, but phi 1 is less than 0, in that case rho 1 is greater than 0, rho 2 is less than 0, rho 3 again greater than 0. So, starting with rho 1 greater than 0, rho k oscillates between plus and minus values. If phi 1 plus theta 1 is less than 0 and phi 1 is also less than 0, then since phi 1 plus theta 1 is less than 0, rho 1 is negative, and again phi 1 is also less than 0. So, rho k oscillates with rho 1 less than 0. For all k greater than or equal to true, rho k decays exponentially in magnitude, just like the autocorrelation function of AR1 process. Here I have plotted the ACF of ARMA11 process, y t equal to phi y t minus 1 plus u t plus theta u t minus 1, and then in the first graph I have selected phi equal to 0.9, theta equal to 0.5. So, in the first graph the autocorrelation function remains positive, but from here onwards it starts decreasing exponentially. In the second case, this is rho 1 and the one is negative, then it remains negative, and in magnitude it is decreasing. The ACF is decreasing in magnitude, but it remains negative, always it remains negative. Actually, this value is for k equal to 0, which is always 1. Again here also this value is for k equal to 0. In third graph, for phi equal to minus 0.5 and theta equal to minus 0.9, the first autocorrelation rho 1 is positive, then it becomes negative rho 2, rho 3 is again positive, rho 4 is negative. So, basically autocorrelation function oscillates, but in magnitude it is declining. Then for phi equal to minus 0.9 and theta equal to minus 0.5, rho 1 is negative, then rho 2 is positive. So, it starts from rho 1 negative, then it becomes positive, again rho 3 is negative, rho 4 positive, and so on. So, the autocorrelation function oscillates starting from negative values, but in magnitude it is decreasing. Now, the ACVF and ACF of ARMA PQ process. So, we have the ARMA PQ process, and if the process is stationary, you can write the process in the form y t equal to theta b upon phi b, u t equal to psi b u t, where psi b is an infinite lag polynomial, summation j equal to 0 to infinity psi j b to the power j u t. So, now we have written this ratio of two finite lag polynomials as a infinite lag polynomial summation phi j b to the power j. Then variance gamma 0 is equal to expectation of y t square. So, you have y t and then you substitute the value of y t here, phi 1 y t minus 1, so on, plus phi p y t minus p, plus u t plus theta 1 u t minus 1, so on, plus theta q u t minus q. So, here you obtain these terms involving products of y t minus 1, y t minus 2, and so on, y t minus p. So, actually here you will get gamma 1, gamma 2, so on, gamma p. Then you also have terms involving expectation of y t u t, expectation of y t u t minus 1, and so on, expectation of y t u t minus q. So, for obtaining these expectations, we write expectation of y t u t minus L equal to, now we write y t equal to summation j equal to 0 to infinity psi j u t minus j, and then you have u t minus L. So, obviously, the only term which has non-zero expectation is for t minus L equal to t minus j or L equal to j. So, for L equal to j, you get psi L, and then you have expectation of u t minus L square, which is sigma square u, and all other terms have expectation 0. So, for all L equal to 0, 1, so on up to q, expectation of y t u t minus L is equal to sigma square u psi L. Then expectation of y t minus L is equal to, again you write y t and y t minus L in this form as infinite like polynomials, and then again you take product of these two and you collect those values which are in square of u t minus j. So, and for the t minus j equal to t minus j dash minus L, you get the square terms. So, you get the terms summation j equal to L to infinity psi j minus L u t minus j square. All other cross product terms have expectation 0. And then finally, you obtain sigma square u summation j equal to L to infinity psi j minus L. So, gamma 0 is equal to sigma square u, you substitute these expectations in this equation for gamma 0. So, you obtain gamma this expression for gamma 0. So, summation L equal to 1 to p, j equal to L to q, phi L psi j minus L plus psi naught plus summation L equal to 1 to q theta L psi L. Similarly, you can obtain the autocovariance function gamma k, which is equal to expectation of u t minus k, and this is equal to we write the value of y t here and multiply it by y t minus k. Then for k between 1 to q, you get gamma k equal to phi 1 gamma k minus 1, which is expectation of y t minus 1 y t minus k, plus phi 2 gamma k minus 2 plus 1 plus phi p gamma k minus p. And then we consider these terms involving u's, and then expectation of these terms after taking product with the y t minus k, you obtain plus sigma square u theta k psi naught plus theta k plus 1 psi 1 plus so on, and then you write it equal to summation L equal to 1 to p phi L gamma k minus L plus sigma square u summation L equal to k to q theta L psi L minus k. So, this is how you can write gamma k in terms of phi's, thetas and psi's, and the autocovariance is gamma k minus L. So, and for k greater than or equal to q, you obtain gamma k equal to phi 1 gamma k minus 1 plus phi 2 gamma k minus 2 plus so on plus phi p gamma k minus p, or you can write it in this summation form also. So, for k greater than or equal to q plus 1, rho k is equal to phi 1 rho k minus 1 so on plus phi p rho k minus p. So, we observe that for k greater than or equal to q plus 1, the ACF of ARMA PQ process just behaves like that of ARP process, because after for k greater than or equal to q plus 1, the auto covariance function or auto correlation function just behaves like that of ARP process, because the effect of moving average term vanishes on the ACF. So, this is where I am going to stop. So, today we have considered the ARMA PQ processes, and then we have derived the autocorrelation function, autocovariance function of ARMA processes. The beauty of ARMA processes is that you can approximate the autoregressive processes or moving average processes of very high order by an ARMA process of much lower order. So, if your autoregressive process or moving average process has a large number of parameters, then while estimating these models of very high order, it may involve large estimation error. Then it is better to use ARMA processes to go for the ARMA processes, because the ARMA processes will have, since the ARMA processes will have lower number of parameters. So, definitely it will reduce the estimation error. Okay, thank you.
Hello, I am A.K. Sharma and I teach sociology in IIT Kanpur. I am trying to answer a simple question: how sociologists explain their facts. As you know that sociology was developed as a subject dealing with human behavior, but which would use the tools and techniques of science, mathematics, physics, chemistry. But this view that human behavior needs to be studied scientifically has been contradicted later on, and it was said that simply by relating one kind of facts with other kinds of facts, you cannot understand human behavior. To understand human behavior or to actually theorize about human behavior, you have to theorize the theories or motivations or meanings that people have in their mind in involving in a particular action. Now, using these two traditions, one tradition in which we relate one fact of society with other facts scientifically, and another tradition in which we try to develop second order constructs or theories that people have in their mind in acting in day to day life. They have produced two different traditions in sociology. One is called quantitative, another is called qualitative. Quantitative methodology uses scientific methods of conducting surveys, censuses, experiments, and then by using statistical methods from simple method like arithmetic mean to sophisticated methods like logistic regression, we try to arrive at some inference. Qualitative tradition, qualitative methodology on the other hand uses ethnographic approach, and here the researcher attempts to become part of the community which he or she intends to study, because the assumption is that only by becoming part of the community, by living among the people whom you are studying, and by putting yourself in their shoes, by trying to understand things or their environment or their behavior or their culture or festivals or economic behavior or politics from their angle, from their perspective, how they feel, what understanding they carry in their mind, that only by understanding these things we can understand facts of society. Actually, in one of the latest works, World Bank, which uses a lot of statistics, has also talked about understanding mental models that people use in involving in behavior. Emile Durkheim long back said that sociology uses comparative method, and let me just give one example and then I will finish. Suppose I tell you that infant mortality rate in India is 40. What does it mean? It means nothing. But when you compare infant mortality of India today with Japan, and you find that Japan has 2 and India has 40, then you get disturbed. Then you start thinking, why is it that infant mortality in India is so high? And then you can also compare infant mortality of India with infant mortality of say Kenya or Mozambique or other countries, and you find that these countries have much higher infant mortality than India. And then you can create a hypothesis that perhaps economic development has something to do with infant mortality. Countries which are more developed, countries like Japan, they have low infant mortality. Countries like Mozambique or Kenya, which are less developed, have higher infant mortality. So, you have a connection. This is what sociology is about, connection between facts. So, by using census, surveys, by conducting field work, by using ethnographic methods, by using comparative methods, we arrive at sociological findings. Use of experimental method in sociology has been very less, but I learned that recently economists, which 10 years ago I could not see that economists will one day use experimental method, but today we find that economists are using lot of experimental methods to study human behavior. Now, this work may be done by economists, but the findings of their study can very well be called sociological studies. So, sociology tomorrow, I think that sociology tomorrow, in addition to using surveys and comparative methods, will also be using experimental methods. Thank you.